ideal world. But realistically, so we do need to take this delay information into account, because in the digital circuits, we are actually, right, this is driven by voltage and current, so we do need to charge and discharge the circuit. So that's where we do have the delay incurred. So for this class, right, we're not, of course, not going to get into the details of some of the analog behavior of the circuits, but we will just make some simple definitions. So we will define something called propagation delay, right? We usually call TPD. Okay, PD means propagation. So this is the delay that we refer to when we look at the time. Okay, so when the input changes, the output will also change, right? But there's usually a delay. The output will not change instantaneously, will not change right away after input change. So there will be a period, right, for the output to respond. That's basically the delay that I just talked about. And if you look at the example here, over here, so input changes, right, from 0 to 1, assuming that's going through some kind of gate. Right? If you look at the standard diagram, so we usually look at the middle point of this 50% of the time of this transition. So this is where the input changes, and we look at when output responds. Right. So this is where the output starts to drop, and this gap or this interval or this specific, right, period, this is the propagation delay. We have TPHL here, which means that the propagation for transition from high to low, HL, right? So going from high to low. And we also have something over here, right? So this is where input changes again. So this is where output goes from L to H, low to high. We have the TPLH. So later on, in most cases, we will not distinguish the transition delay between two different kinds of transitions, HL, H to L, L to H. In most cases, we'll just assume that they are equivalent, but we do have something called minimum delay and maximum delay. So minimum delay usually is called, in some cases, we call it contamination delay. It's going to be clear in the next lecture. And the maximum delay, we call it propagation delay. Right? So the reason is, it's not just a single delay number, because we have a circuit, right? In some cases, signal may travel through the short path, right? That's where we have the minimum delay, right? When we look at the short path, then we look at the long path, we have the max delay. And also, even for a single gate, depending on the actual temperature, right, of the circuit, so the delay may actually vary a bit. So that's where usually there's this band. So we have in the spec, we have both a minimum delay and maximum delay. Right, again, this is not too important right now for this lecture. So in this lecture, we just assume a single delay number, okay, which is just a propagation delay. Let's look at a more concrete example. And this is actually something that you guys saw. This circuit is something that you guys saw in Purium 1 as well. Right. What is this circuit? What is this building block? This is a conventional building block, right? What is this? Very good, Ambrose. This is a mux, right? Q1 mux. We have some intermediate signals. Okay, S, right? This is where we make the choice between two inputs, right? As S0 and X, right? And S and Y. So if you look at the corresponding timing diagram, this is a waveform, right? But now I'm actually adding delay information in this waveform. So if you look at this diagram, we have X, right? X is the input, X is staying at high for a while, right? And Y is staying at high for a while, and then Y drops. Okay. So S is staying high in this case. So if you look at this specific case, right? So since Y drops, S and Y, which is this signal, S and Y, it's also supposed to change, right? It's not changing right away. Okay, there's actually a gap. So what is this gap? Can you guys tell me intuitively what's the meaning of this gap? What does this gap represent? The TBD, very good. Emily, TBD of what? the propagation delay of what kind of thing? The AND gate, right? Very good. This is basically the TBD, right? The propagation delay of that AND gate. We are doing S and Y. Okay, so this is what the gap is coming from. Hopefully this is clear. Okay, this is the timing diagram. And actually not, this is actually expected change, right? So, you know, when Y changes, so S and Y, this intermediate signal also changes. But in fact, there is something called glitch. We use glitch quite often, right, in daily life as well, right? Which means something that's unexpected, right? This is something that unplanned. So it turns out that the moment that we consider this propagation delays, right, the moment we have this timing involved, we may see some of these unexpected changes in our circuits. Usually we have three kind of glitches. There's something called type 1, static 1 hazard. This is where the output is supposed to stay at high or 1, okay, all time, but somehow there's this dip. This is a transient or this temporary dip to 0, and then we'll go back to 1. This is called the static 1 hazard. And similarly, we have this 0 hazard, a static 0 hazard. So this is where I was supposed to be 0, but there's this spike, right, to 1. Again, temporarily. So just this is a transient. And we have something called dynamic. This is where the output actually changes more than once. It's supposed to change maybe just once, but it changes more than once. Okay, so this seems counterintuitive, right? This may not be immediately clear to you guys. Why somehow, right? So all of a sudden, you know, we are supposed to have this perfect circuit, right? Which is supposed to be outputting 1, but somehow because of the delay, the propagation delay, there's this temporary dip or spike. Why is that the case? So let's look at the concrete example. Again, let's look at this 2-to-1 mux. First, all the way agreed, right? So this is a 2-to-1 mux. X and Y, they are the two inputs, right? We are selecting from one of them using S. So here's my assumption. Assume that X and Y stay at 1. And S makes changes from 1 to 0. So question for you guys, is F supposed to change or not? Without considering the delay. What is F? Always 1, very good. Because we are doing mux, right? We are selecting either X or Y, but both X and Y, they are 1. So it doesn't really matter whether S is 0 or 1. So F is supposed to be 1. Okay, hopefully you guys agree. So we are supposed to have a 1 on the output side. But now let's look at some of the interesting behavior from the circuit. So first, okay, I'm assigning the values, right, on these signals on these wires, right? S is 1 initially, right? X is 1, Y is 1. Of course, this wire is 1. This signal is 0, right? After the inversion, and we have 0 here, right? 1 here, and 1 here, right, on the opposite side. So now that S, this guy, right, the select signal, is making a change from 1 to 0. So I'm assuming that all these gates, if you look at all these gates, right, we have inverter, AND gate, and OR gate, right? So I'm assuming that the propagation delay of these gates are all 1 nanosecond, right? Nanosecond is 10 to the minus 9 seconds, right? Assuming this is the case, okay? Actually, in today's circuit, it's much shorter, the delay. So basically uniform, right? I have a uniform delay for this case, right? Initially, so S is 1, and then it's making changes to 0. So what's gonna be the output, right? So let's look at some intermediate signal. What's gonna be the value of those intermediate signals in the next nanosecond? So for this inverter, right? You know, this guy, right? Of course, gonna make a transition from 0 to 1. Right? And here for this AND, it's going to make a transition from 1 to 0, right? Because the input changes from 1 to 0 already, right? In the next nanosecond, S and Y will become 0. And this one, right? There's no change here. Oh no, there's a change here as well, because in the next, right, in the next nanosecond, but initially no change here, right? So first we look at the inverter, in the, let's say, right, so we use time the second, let's just say nanosecond, the second timestamp. How about that, right? Each timestamp means each period is 1 nanosecond. So first the inverter make changes, right, from 1 to 0 to 1 over here. Okay, and basically in time, so we are looking at time 2, right? Time 2, I'm using timestamp. Time 2 really means the second nanosecond, right? Time 2. So these are the values, right? Okay, so any questions so far? Okay. Right, very good question. Ambrose, so is there a delay on the wire? Yes, but in our world, in the 2300 world, so we're gonna just assume that all the wires take 0 delay. And this is actually an absolutely false assumption. Okay, and in real world, the wire delay are very important. So we also need to consider the wire delay. But just for the sake of simplicity, so let's just focus on the gate delay first. Okay? And all the wire delays are 0. Okay, basically no wire delay. Okay, so what's gonna happen? What's gonna be this value? So in the next nanosecond, in time 3, it's gonna change to 1, right? And at the same time, in time 3, so F is making a change from 1 to 0. Is this clear to you guys? Why is that the case? So first, so this might be a little bit confusing, right? So this is time 2, right? And this is also time 2. Because of propagation delay, so this guy is still 0, right? So this is still 0 because we are propagating the change of S over here, right? In time 2. So in time 1, this is time 1. So this signal is still 0. So that's why in time 2, right, this signal is still 0. Okay. And that's where in time 3, so this is really time 3, F is dipping to 0. Because we have 0 here, right, in time 2, and 0 here in time 2. Okay, are you guys following? Right. If not, just look at this. Just try to propagate the signal, right, through this circuit. And of course, finally, right. So finally, so we have a 1 here. So at time 3, this is also time 3. This is basically the 3rd nanosecond. And in the 4th nanosecond, time 4, F gets back to 1. This is time 4. Okay. Any questions? So this is where we have a glitch. Right. So one more time, right? The output signal is supposed to stay at 1, but there's a transient, right? So there's a transient, which is this is where we have a dip. We have a 0. Okay. On the diagram, if you draw the timing diagram, so the glitch is like this, right? it's not going to be always 1. So we have this static 1 hazard. All right. So now is the question is this a worrisome? Right? Is this something that we have to be concerned about? Actually, the answer is usually this is fine, because we are using flip-flops and we are using clocks. So usually the inputs are connected to the flip-flops, and also the outputs are connected to the flip-flops. And we sample the changes at the clock edges. Right? As long as the glitch does not happen at the clock edge, we are fine. This is actually why, this is the reason that we really want to make use of the flip-flops to capture the states, to capture the state of the circuit, because it's edge sensitive. Okay. Of course, the clock right, must be a special signal. This is not something that we are going to get into. We will use a glitch-free, almost glitch-free signal. So we have a special circuitry to generate clock. But for this output signals, right, from the logic, from the conditional logic, it's fine for it to have a glitch, as long as it does not happen right before the clock edge, the triggering clock edge. In this case, the rising clock edge. Right. And if this is not too clear, right? So here's the timing diagram. Right. You know, we have these mux, right, being sandwiched by 2 flip-flops. And this is the clock, right? You know, we are using rising edges. These green lines indicates where the clock edge happens, right, occurs. Between these green edges, right, these green lines, we have the cycle, right? Each one indicates a cycle. So see here, right? Now we basically sample, we only sample the F, right, over here around the clock edge. So this is the important thing. That's why we want to use the D flip-flops, right? The edge sensitive device. And if there's indeed a glitch, okay, as long as it does not happen right at the clock edge or right before the clock edge, this glitch is totally fine, because it's gonna restabilize, right, to 1. And then that's where we're gonna capture the right value. Any questions so far about the glitch? Okay. Right. So if not, okay. Next time we're actually going to talk about. So this is fine, right? So you know, this is actually happening inside the cycle time, in the middle. Next time we're going to talk about, right? So what are the cases we have to avoid? We don't want this glitch to happen right before the clock edge. There's something called setup time, and this is something that we're going to introduce in the next lecture. All right. And this is an important notion. This is an important concept. It's called the synchronous circuits. We are using synchronous circuits in our class, in our lecture. So we are not, so basically, which means that the whole circuit is synchronized by a clock. And we have many, right? So we have many sequential logic, right? We have many complex logic. They're all running in parallel. But what's happening is that, so we only capture the states, right? We only update the states of our system at the clock edge, right? Using the flip-flops. So that's why it's called the synchronous. And this is the precise reason that we want to use the flip-flop. And because we want to avoid the implication of the glitches. Okay, so since we have 1 more minute, maybe I can ask you guys 1 more question. So what if we replace this one with a latch? Does the glitch matter or not? If you replace it with a latch, D-latch. Yes, right. Okay, but very good. So, but maybe let me ask you a follow-up question. So, but this is gonna stabilize, right? So even though there's this dip, right, temporal dip, it's going to restabilize to 1. And eventually this latch will capture 1, right? During this, if there's still a cycle, right, during the cycle time. But why is this still bad? Why is this still a problem? Right, I always basically asking the same question. Right, it's going to go back to normal. Why is that the problem? Yeah, it's level sensitive, right, Jacob? It is level sensitive. That's why the glitch will be captured by the latch for a certain period of time, right? But almost question is also my follow-up question is, but it's going to come back up to 1. So basically it's going to be, so the eventually, right? Hopefully eventually, so this latch will capture the correct value. But why should we still be concerned? Right. Okay. Very good, guys. Because this latch may connect to other computer logic, right? This may connect to other part of the system. So the moment that a glitch is captured by a latch, this error, right, may propagate, and this may be out of control eventually. Okay. All right. So very good discussion. Okay, right. So Emily, you're basically saying the same thing, right? There could be other more additional logic that's connecting to this latch. So, and the moment we capture that, since it's a level sensitive, it's going to propagate. Okay, great. I think we are done. Guys, see you guys next Tuesday.